So this is the slotted line lab, and in this lab you'll learn how to use a 50 ohm slotted line crystal detector and standing wave ratio meter to obtain the wavelength and voltage standing wave ratio on a coaxial transmission line. So here we have the slotted line meter. You want to make sure that this cover is tilted down so that you can move the slotted line along with this knob here. This is a standing wave ratio meter. You want to make sure it starts out at 0 right here, the gain, or the decibels, and you have your signal generator here. So the way that you use this is that you connect different loads. These are the different loads. This is the open load. It looks like this. The 50 ohm match load looks like this. The short looks like this. So the difference between the open, the short is covered here and the open is open. And the unknown load looks like this. So the way you connect a load is you can see there's teeth in this outer rim of the load, and there's matching teeth on the end of the slotted line. So you want to first pull this metal part back and make sure that the teeth are aligned, and then you press on it, and then you just screw on the load and make sure it's tight. And then the way you measure the wavelength is first you want to, so that this measures the wavelength along what looks like the absolute value of a sine wave. So your maximums and minimums will be 1/4 of a wavelength apart. And you can see on the slotted line meter there being maximums and minimums. So the first thing you want to do is normalize this to the load. So you want this to be at 0 dB at the maximum. So you do that by adjusting the gain. So you move the line along until you think you've got a maximum. But I'm moving it along just by twisting this knob, and I'm adjusting the gain. So you can see here, this is a maximum, but I want the maximum to occur at 0 dB, so I'm just going to adjust the gain a little bit. So after I do that, I can find a minimum by going down the line. So also the maximum I can see here, I can just read off the centimeters that it occurs at. So this occurs, and I have the short connected, it occurs at like 16.8-ish centimeters. And I'm going to move down and try and find a minimum. So I've gone past my scale here, so what I want to do is I want to refine the meter a little bit and move down to 10 dB, and you'll see this pops up. It's important not to switch this down to a higher decibel level if it's not past the 10, past the left side completely, or else the needle will swing forward and it's kind of breakable. So now I see I've gone past, I can go past the 10 again, so I refine it a little bit more. And the more you refine it, the more sensitive it is. So it kind of drifts too. So if you can see it kind of swung up. So this is probably a minimum here. I think that's safe to say that this is where the minimum occurs at like 29 centimeters. So the wavelength of this is the maximum minus the minimum. So 17, or 29 minus 17 divided by 4 is the wavelength of this particular line. And so you go through the different loads and calculate the different wavelengths. The match load should not have any maximum or minimas since there shouldn't be any reflections. I think that's pretty much it.